This is the video lecture of Math 4500, Partial Differential Equation, Chapter 1, Section 1. So, Chapter 1 is first order linear PDE. First order linear PDE. And Section 1.1 is just introduction. Okay? All right. So first of all, what is partial differential equation? Okay. I'm going to use this one. What is partial differential equation? An equation which involves partial derivative of unknown quantity. All right? An equation, EQ stands for equation. This is about, see, an equation involving partial derivative of unknown quantity, unknown, is called a partial differential equations. In short, we call it PDE, partial differential equations. Now, in order to have a partial derivative of unknown quantity, that unknown quantity must be depending on multiple variable. All right? Otherwise, there would be no partial derivatives, which is quite common. You know, it is very rare that certain quantity depends on only one variable. So, for example, temperature distribution. The temperature depends on the location and time. Your location has x, y, z coordinates, time, t, so it involves actually up to 4 variables, right? All right, some examples. Example 1, A, round u, round t, plus c times round u, round x equals 0. This is so-called advection equation or linear transport equation. Okay? So let me equation. Now B, round u, round t. So u is a function of x and t, all right? And x partial and y partial has this relation. We call it linear transport equation or advection equation. Round u, round t minus alpha, round square u, round x square. Plus u times round u, round x. We call it Burger's equation. One D means one-dimensional spatial variable. Of course, you have x into 2 variables of u, but 1D spatial variable. T is time. 1D Burger's equation. C, round u, round t. For all of this case, u is the unknown variable, unknown quantity. We want to find the solution of. Round u, round t minus alpha, round square u, round x squared equals 0. This is 1D heat equation. 1D heat equation. EQ stands for equation, heat equation. D. subscript notation is, another way of writing partial derivative. This is second order partial derivative u with respect to t squared, twice, right? Second order derivative. U sub tt minus some constant beta u sub xx. This is 1D wave equation. Sometimes they call it actually diffusion equation. Diffusion equation or heat equation. This is wave equation. In this case, second order partial derivative with respect to t. This is first order partial derivative. That's the biggest difference between this and that. Right? E Laplace u, which is u sub xx plus u sub z equals 0. Okay? Wow, this is called delta u, or Laplace of u, Laplacian of u. This is 3D Laplace equation. U sub xx plus u sub y equals. So this is some known function, given function, not an unknown quantity you're looking for. Some given function of xy are independent variable. U is the unknown. This is called Poisson equation. 2D Poisson's equation. G Laplacian u minus lambda u equals 0. We call it Helmholtz equation. H u sub t minus Laplace of u, Laplacian of u, f of u, reaction diffusion equation. Reaction diffusion equation. Okay? All right. F is some nonlinear function. Here, capital F is a nonlinear function of one variable. Like f of z equals z squared. So f of u means u squared. If f is sine of u, then f of z equals sine of z, then f of u means sine of u, right? Some non-linear function of one variable. Okay, then we call it reaction diffusion equation. So these are, there are hundreds of partial differential equations are used in application. But these are some of those famous examples of those equations. Okay? Now, classification. Of PDE. First of all, we can make a linear PDE versus non-linear PDE. Linear in terms of unknown and its derivatives, partial derivatives. So for example, with respect to unknown and unknowns partial derivative, this is 1 and 6. It's a linear combination, right? This is linear. A. U times round this. Unknown and another unknown thing multiply. Just like x times y. That's not linear term. Non-linear. C. Well, unknowns partial derivative, unknown partial derivative, linear combination. So this is linear. Also linear. This is also linear. f is linear. Now, this can be nonlinear function. When we say linear PDE or nonlinear PDE or ODE, same thing. It's not about this given function or even coefficient function. It is about unknown. So for example, if you have a u squared round to x minus sine of y round of u round y equals let's say e to the xy. This is linear PDE because your given functions are considered just like a constant. It's a linear combination with respect to unknowns, right? Or you could have one more. So y cubed u equals sine of e to the xy. Okay. In terms of u and round u sub x, u sub. So it's not about the coefficient function known given function. It is about unknown. All right. So this is also linear. G is also linear. H is not, because your capital F is a non-linear function of u here. Okay? U is in B and H is non-linear. Among the linear ones, PDEs, there are homogeneous. Or non-homogeneous. We talk about homogeneous or non-homogeneous only among linear PDE. Homogeneous is when you have all the unknowns on the left-hand side. All the terms involving unknown and its derivative. Right-hand side is constant zeros. So B is not linear, so we don't consider this homogeneous. C, right? D, E, and G. These are homogeneous because you have zero on the right hand side. When you collect all the terms involving unknown and its derivative on the left hand side, right hand side, zero. On the other hand, this one, F, is non-homogeneous. Okay? Non-homogeneous linear. All right. Historical development, I'm going to just say it, all right? Obviously, the earliest approach to partial differential equation were motivated by the effort of solving concrete problems, starting with physics, right? Maxwell's equation is a PDE, okay? Partial differential equation of electric field and magnetic field. So the earliest approach to PDE is actually trying to find formulas of a solution for given partial differential equation with, initial conditions and boundary conditions. All right, actually finding a concrete form of a algebraic expression describing the solution behaviors. Right, basically formula of a solution using a lot of techniques. So they developed, in that effort, they developed some concepts of Fourier series and basically orthogonal function series, Fourier transform, Laplace transform. All of these were invented in that process. But later, mathematics start paying attention to more fundamental questions. They realized that some partial differential equations don't seem to have a solution at all with the given initial condition, boundary condition, or some solution may have many solutions. All right. So they develop a general theory about linear. This theory about existence and uniqueness of solution, and well-posedness. Well-posed means that if your boundary condition changes slightly, does it make your solution changes dramatically or also slightly? If it is also, so the solution behavior with slightly different boundary condition is only slightly changed. We call it well posed. That means it is physically feasible solution. Okay? So that kind of uniqueness, existence and uniqueness and well posedness of solutions of linear PDE. And then the modern approach is to build a general theory of some important nonlinear equation too. There are some also theory, like one of them is minimum principle, calculus of variation. Those stuff are also some of the well-known techniques in that effort for non-linear partial differential equation. In this course, we'll mainly we'll learn some general properties, some framework, mathematical framework to see the PDE, not just delve into finding solutions, but some general framework, terminologies. But in the end, our main focus will be actually finding solutions of important linear PDEs. Okay, and then I will introduce some taste of some more general theories behind those. All right, because it is the introduction course, the first course on PDE in undergraduate level. Okay, so that would be the first section. Now, section 1, 2. Is linearity and superposition principle. Linearity and superposition principle. Actually, superposition principle and linearity are the same thing. Okay? So, definition. An operator L is called linear if and only if the following is true. L of C1 U1 plus C2 U2 equals L C1 L of U1 C2 L of U2. For all, this stands for all, right? For all. A from all, right? Capital A upside down. For all, C1 and C2 in the real number system. You know, this means belongs to. In set theoretical notation, belongs to. The boldface R is the set of all real numbers. So for all C1 and C2 belonging to the set of real number, which means for all real number C1 and C2, and for all, functions. For all functions, U1 and U2. Well, certain functions. So operator, I call it operator. Operator is just a function whose input is another function like U, or U1 and U2. We call it operator. Operator is just fancy name for a function whose input or whose domain is set of certain type of functions. Okay? So, if an operator satisfies this condition, so basically your operator can be split over addition of functions, constant multiple can be taken out of the operator. We call it linear operator, a linear operator. Example 1, A. For any differentiable function, U on an interval AB, define L as L of U equals d over dx. So basically L is d over dx. Okay, I can write L as this. The derivative of. So this is an operator, differentiable operator. Okay? You take an input function, you give its derivative as an output. Okay? Then it is a linear operator. Why? What is it? L of C1, look at this. Because this three dots is because L of C1U1 plus C2U2 is the derivative of C1U1 C2U2. Well, we know that derivative has this property. C1 du1 dx plus C2 du2 dx. We know that differentiation can be split over addition and constant multiplication can be taken out. That's C1 L of U1. So this very basic property we already learned in calculus 1 is nothing but linearity of this differential operator, right? So we are already very familiar with this linearity of an operator. And of course, likewise, for any integrable function, u on AB, define L as this is a definite integral, right? Of u from A to B. Then, you know, definite integral of L of C1U1 plus C2U2. Definite integral can be split over addition and scalar multiplication. So this is also linear, all right? Then L is also linear, all right? What about C? What is C? C. For any twice differentiable function u of xt, a function of x and t, define L as L of u equals round u round t minus alpha round square u round x squared. Or a lot of times we write it d sub t u minus alpha d x x u, right? Now, that means your L can be written round t minus alpha round square round x squared. Okay? This is differential operator because it involves the derivative of the input function, right? Then it is also linear operator. It is a linear operator. Linear. We can prove this one. When we have a C1U1 plus C2U2, then what does it say? Round t of this one, C1U1 plus C2U2 minus alpha partial square with respect to x twice of C1U1 plus C2U2. Then round t as a differentiation with respect to t, this can split over addition and constant multiplication. Same thing, second order partial derivative, also linear, minus alpha, and then over here, C1 x squared, C2 C2, right? And then I can collect C1 round U1 round T, C1 minus alpha if you distribute and factor out C1 minus alpha round square U1 round X squared. Factor out C2 and round U2 over round T. C2 factor minus alpha times this. So what is it? This is C1 L of U1, C2 L of U2 for all C1 and C2 and U1 and U2. So this is linear operator itself. Linear operator, just like this. All right? A linear combination linear operator will be linear operator too. If you had taken linear algebra, you already learned this one as a general theorem, right? Linear combination of linear operators will be another linear operator. This is what we're talking about here. Now, if you look at remark, for this one, L of U equals 0. So we learned in the previous section, what did you learn? Round U round T minus alphas round square root. That was a heat equation, right? Heat equation. Now you can write this one as L of U equals 0 with this L, right? With this L. So we can write this linear PDE as this equation, simple. L of U equals 0. L is partial differential linear operator. Okay, for this one. And obviously, if we define 1, 2, if we define L equals this one, then this 2D Poisson equation in the previous section we learned that this is 2D Poisson equation, right? You can write this one as L of U equals f of x, okay? So this linear operator, differential operator notation can be very useful in studying partial differential equations, okay? All right, now let me check recording for a moment. All right. Okay. Now, remark, okay, definition maybe. If L is a linear partial differential operator, just like this, okay, or like this, then, and f is a known function of independent variables, then L of U equals f is a linear PDE, and the equation L of U equals 0 star equation is called the associated homogeneous equation. equation of the star, right? When you replace right hand side with 0, it becomes associated homogeneous linear PDE. Okay? Now, theorem 1. Superposition principle number 1. So, let L of u equals 0 be a homogeneous linear PDE. Homogeneous linear PDE. That means L is a linear partial differential operator. If U1 and U2 are solutions to this linear homogeneous partial differential equations, then any linear combination of those two, C1 U1 plus C2 U2, is also a solution to of this same homogeneous partial linear differential equation, linear partial differential equation. Okay? For all C1 and C2, all real number. Okay? So if you know two solutions for linear homogeneous partial differential equation, you can get infinitely many solutions by having linear combination like this. This is what we call superposition principle 1. The proof is simple. It's just a linearity in the end. So, okay. So U1 and U2 are solutions. Okay? Suppose you need a solution. What does it mean? That is, i.e., L of U1 equals 0 and L of U2 equals 0. When you actually substitute U1 and U2 for unknown variable, you get actually equals 0, identically 0. Alright? Now, how do we show that C1 U1 plus C2 U2 is also a solution? How do you show? It is a solution if L of that equals 0, right? Being a solution of this one means when you have L of that function, then being equals 0 identically, then this is a solution. So let's consider L of C1 U1 plus C2 U2. Now, because it's linear PDE, this is a linear operator. Because it is a linear operator, this is C1 L of U1, C2 L of U2. Now, because U1 and U2 are solutions to the same equation, so we know that L of U1 equals 0 identically. This is also 0 identically because U2 is also a solution. So you get 0 for this. That's why C1 U1 plus C2 U2 is all a solution too. Okay? So this linearity is everything. Alright? Now, same thing for the next version of superposition principle. Theorem 2. Superposition principle. Second version, more general version. So, let's say let L be a linear partial differential operator. Partial differential operator. Okay? And F1, F2 are known or given functions. Okay? Given functions of independent variable, obviously. All right. Now, if U1 is a solution of the following non-homogeneous linear PDE, F1, and U2 is a solution of another non-homogeneous equation where left-hand side has the same structure as a PDE, only the right-hand side functions are different. Okay? Then linear combination C1U1 plus C2U2 is, if that is the case, then C1U1 plus C2U2 will be a solution of L of U, again same left hand side of the differential equation, but right hand side will be C1F1 plus C2F2. Okay? So, the proof is also same. In order to show that this is a solution to this differential equation, you just have to show that L of that function will satisfy this. Alright? Now, since L1, suppose that U1, okay, suppose this one, okay? Suppose that U1 is a solution of this and U2 is a solution of that. That means, i.e., that means L of U1 equals F1, right? L of U2 equals F2. Actually, when you plug it in, U1, you will get identity with F1. Same thing for U2 with F2. Now, in order to show that this is a solution of this new differential equation, what do you have to show? L of this one is being equal to this, identical, right? Now let's think about it. Again, because it is a linear operator, we can split over addition and constant multiple. Now we got that this is F1, so this is C1, F1, this is F2. Hey, this is a solution then, right? Oops. Plus C2U2 is a solution of this equation. Okay? Again, just linearity. So superposition principle is basically the phenomena occurs due to linearity. Alright? So we can only use superposition principle only for linear PDE. Alright? And superposition principle will be crucial, very important part of solution finding process in linear PDE. And that's what make linear PDE so much more preferable or easier to solve. Okay? So the first two sections are basically introductory sections, preparation. So we're done for the video lecture for section 1.1 and 1.2. All right, in the next section, I'm going to derive linear transport equation. All right, see you next time. Bye.